Okay, we are live. Hello, students. Can you let me know before starting this session? Am I visible and audible to you? Please let me know with a thumbs up in the chat box. Hi, everybody. Welcome back to Vedantu JEE English channel. Hi, Yashwant. Hi, Hardeep. You want digital board? Bacha, this is a digital board. Good evening. Hi. Hi, Sarada. Hi, Hari Varshini. Hi, Omji Magic Tricks. I know everybody is just waiting for the results right now as I can see the chat. Hi, Mani. Hi, Denizen. Everybody, welcome back to this session. So, I know you are eagerly waiting for the results. I know, but do not stop working towards your April attempt because this time results are going to be all over the place as the paper came out to be really easier on the easier end this time. So you have to prepare for your April attempt with much more enthusiasm now. So looking at the trend of your previous JEE paper in the January, we now know that biomolecules is an important section to cover. You can no longer ignore this chapter once again because in each session there were at least 2 questions asked from this chapter. So we are going to cover the entire chapter within 1.5 hours today. We're going to complete from the starting to the end, leaving nothing. I'm going to explain to you everything, every structure, every stereochemistry, every reaction, and what are epimers, anomers, proteins, carbohydrates, fats, everything we are going to study in this chapter. Now, why is this chapter so important? And first of all, most importantly, why is it interesting? Acha, okay, before moving on to that, if you have just joined the chat, please like the session and share and also subscribe the channel if you're not subscribed yet. Okay, hi, beta, this is organic section only. We are going to finish organic within the next week. This is my within this week we're going to finish the entire organic part. The majority of the part we're going to finish in this week. Okay, but now why is this session so important? Because bacha, this biomolecules chapter is actually related to what? To your everyday life. What do you do every day? Eat. And whatever you eat is made up of biomolecules. Why? Because whatever you eat has what in it? It has carbohydrates, it has fats, it has proteins, it has lipids, it has vitamins, it has minerals. What are all these? These are all your biomolecules. So whatever you are eating is nothing but a biomolecule. As you can see, this is a food pyramid on your screen right now. So food pyramids consist of complex carbohydrates, your fruits, your berries, your vegetables, your proteins, everything. We're going to talk about what is your food made up of in this session. So it is extremely interesting. What is carbohydrate structure? So we are going to talk about the chemistry of it, not the food importance or the nutritional value of it, because that comes in a whole other subject which is called the nutritional subject. But here we're going to learn even more interesting their biochemistry of it. Like what are carbohydrates actually made up of? Like what is the structure of protein and why is it so important, and everything we're going to learn in this session. Okay, let us start. Ma'am, I got 88% people are actually talking about the results right now. Okay, next. So first of all, bacha, as I told you, the food pyramid consists of too many things. But in your course, you're very lucky. You just have 3 things to study. One is carbohydrates. The second one is your proteins. And the third one is your nucleic acid. Only these 3 kinds of biomolecules we are going to read. So we're going to start with carbohydrates. So as the name suggests, what do you think the name suggests here? The carbo means carbon and hydrate means water. Okay? So this is an older definition of carbohydrate where people thought that carbohydrates are those compounds which are hydrates of carbon. For example, any compound, any molecule which follows this formula, which is like some C will be there and some water molecule will be there. So CxH2OY should be their molecular formula. So anything which had this molecular formula was supposed to be a carbohydrate. For example, what is the molecular formula of glucose or fructose? It is C6H12O6, and I can write this formula as C to the power 6 and H2O to the subscript 6 again, right? So this is a hydrate of carbon once again. Now let's look at sucrose. The structure of sucrose, the molecular formula of sucrose is C12H22O11. I can again write this formula in the form of C to the power 12 and H2O to the power 11, and I will get this formula. So in these two kinds of sugars, carbohydrates are basically known as sugars, correct? This is their common name. So all these sugars, most of the sugars can be written in this formula, which is called a hydrate of carbon. But there's a very big but here. The but is, for example, look at the formula for acetic acid. I can write the formula of acetic acid as C2H2O to the power 2. Okay, so again I am writing C to the power something and H2 to the power something. But again, is acetic acid a carbohydrate? No, this is not a carbohydrate, even though it is following the previous definition of carbohydrate, which is C to the power X and H2O to the power X. Still it is not a carbohydrate, remember this. But again there is some other exception. For example, look at the structure of ramenose. This is again another type of sugar or another type of carbohydrate. Look at this molecular formula. The molecular formula is C6H12O5, and this formula cannot be written as the formula of C6 C to the power X and H2 to the power Y. It cannot be written in this form. Still it is what? A carbohydrate. So can you see the previous definition which thought that carbohydrates are those molecules where there is a carbon, some amount of carbon, and there is a hydrate of it. But this definition actually fails using these two examples. Hence, we have to come up with a newer definition which is universally applicable, right? Which should have no exceptions to it. Therefore, the modern definition now is carbohydrates, are those molecules which are optically active. Remember this term. All carbohydrates are optically active, means they have a chiral carbon in them, which means there is no symmetry in them, right? They're optically active polyhydroxy. Polyhydroxy means there are too many OH groups attached. For example, OH, and then again there will be C and again an OH group, again there will be C and again an OH group. So just like this, there will be too many OH groups attached, and a aldehyde or a ketone group will be there. So these are what the criteria of a carbohydrate. Number first, should be optically active. Number second, should have too many OH groups in it. More than one, more than two OH groups will be there. Then they should have a functional group of what? Of either an aldehyde or a ketone. Both of them will not be together. There will be either aldehyde or ketones. Okay? Aldehyde means a CHO group or a ketone group will be there. So this is the new definition of carbohydrate. They should have all these things in it, or they should produce such compounds on hydrolysis. Hydrolysis means what? When I try to break the structure using water molecules. Correct? So this is called Beta, this is a live session, not a recorded session. Okay? You can ask me questions right now, whatever doubts you have. I'll be looking at the chat box and clearing your doubts. You understood this new year definition of carbohydrates? Let's move forward. What are the classification of carbohydrates? So, there are too many bases on which we classify carbohydrates. Number first is on the basis of functional group. Means what? I just told you they can either have a aldehyde group or a ketone group, right? So they're classified on these two bases. For example, if it is a polyhydroxy aldehyde, example is glucose, or it can be a polyhydroxy ketone, example is fructose. Simple. Number first classification clear on the basis of functional group attached to it. Now let's move on to the second classification, which is on the basis of reducing sugar. Now, ma'am, what is a reducing sugar? So, I will teach you what are reducing sugars later on in the chapter. Right now, just focus. Okay, there's a term called reducing sugar, and I need to just keep it in my brain, and I will explain it to you when the time comes. So, this is the second basis of classification. Number first is a non-reducing sugar, example sucrose, and number two is a reducing sugar. And the examples are fructose, glucose, maltose, lactose, and all the monosaccharides. Now, ma'am, what are the structures of these compounds? We will learn one by one. But right now, focus on what I'm teaching. So, two classifications we have learned. Number first on the basis of functional group. Number second on the basis of are the sugars reducing or non-reducing. Okay, and lactose, maltose, and sucrose given here are your disaccharides. Now, what are disaccharides, monosaccharides? We will learn in just a while. Next classification is on the basis of sweetness, right? The sugar that you eat in the morning that you just mix in your milk and drink it. What sugar is that? That sugar that you drink every day in the morning is sucrose sugar. Isn't it sweet? It's sweet, right? So, many of the carbohydrates are sweet. Okay? So, therefore, they are classified as sugars, which means which are sweet, and the non-sugars which are not sweet. For example, the cell wall of plants is made up of cellulose, which is not a sweet sugar. Right? So, on the basis of sweetness also, again, it is classified. Okay? And saccharide came from a Latin word named saccharum, which means sugar. Remember this thing? And number fourth and the last classification is on the basis of carbon atoms. Remember this. The simplest sugar, remember this, the simplest sugar is made up of 3 carbon atoms. There is no sugar lesser than 3 carbon atoms present anywhere. Remember this. The carbohydrates start with 3 carbon atoms, the smallest chain of a carbohydrate. Remember this, I'm writing it here. The smallest chain of a carbohydrate consists of 3 carbon atoms. And why? I will teach you just now. See, it can be on the basis of carbon atoms. For example, if there are 3 carbon atoms, it is called triose. If there are 4, it is called tetrose. If there are 5, it is called pentose. 6 is it is called hexose sugar. Okay, understood? Okay, tetra means 4 and O's. Whenever you see a O's suffix is something we attach at the end. So whenever there is O's written anywhere, just understand that it means a sugar is present there. Okay, next is CHO. For example, if now this is the number of carbon atoms. Now to the 3 carbon atoms, the functional group attached is a aldehyde. Then it will be called a aldose. And if the functional group attached is a ketone, it is called a ketose. For example, if a carbohydrate has 4 carbon atoms and an aldehyde group, it is called aldopentose. Why it is called? Because 4 carbon atoms plus a CHO group. Can you see? 4 carbon plus 1 is 5. So it is aldopentose. Or if a carbohydrate has 5 carbon atoms and a ketone group, then it is called a ketohexose. Why? Because the functional group is a keto group. And how many carbon atoms are there? 5 plus 1, 6 carbon atoms. Okay? Now I will make you understand why there are 3. The smallest unit of a sugar consists of 3 carbon atoms, because understand this. For example, if the functional group is a what group bacha? Aldehyde, then the aldehyde group bacha is always a terminal functional group. So now I know that this group will be there. Okay? Now the next criteria for a sugar was what? The next criteria was it will be a polyhydroxy. Polyhydroxy means there will be more than one OH group. So there is one OH group, the second OH group will definitely be here, right? So there should be more than one OH group and one functional group present. So can you see? To satisfy the conditions for the definition of a carbohydrate, the minimum chain, the smallest chain of every carbohydrate needs to have 3 carbons at least to satisfy the definition. Similarly, for a ketose sugar, there will be a ketone group here, and again carbon here, it will be OH group here, one OH group here. So can you see, only and only if 3 carbon atom chain is present, only and only then the definition of a carbohydrate is satisfied. Because what was the definition? That, look at the definition again. Definition is there should be a polyhydroxyaldehyde or ketone. Okay? So only in this manner that definition is satisfied. Everybody understood? Next, move on to the next thing, which is a classification of carbohydrate on the basis of the number of products of hydrolysis. Number of products of hydrolysis means what? For example, I have a sugar molecule, okay? And that sugar molecule, for example, it does not undergo any hydrolysis. Now I know that this is my carbon chain, okay? So sometimes this carbon chain will not undergo hydrolysis, therefore they are called monosaccharides. Oligosaccharides is when I put my sugar, when I put the carbohydrate in water, what happens? It gets broken down into units, into individual units. And if the number of the units is 2 to 10, then it is called a oligosaccharide. And a polysaccharide means when I dissolve my carbohydrate in water and the carbohydrate breaks down into more than 10 units, then it is called a polysaccharide sugar. Okay? Next thing is sources, which is monosaccharides. For example, what are the examples of monosaccharides? These are the names. I will teach you the structures just right now. Stay with me. For example, monosaccharides, glucose, fructose, galactose. Oligosaccharides examples are sucrose, lactose, maltose. All these are disaccharides, right? And your polysaccharides examples are starch, cellulose and glycogen. Important examples are all given in this table. Important examples what all are asked in your exam. Now next is for a typical polysaccharide. What happens for a typical polysaccharide? It is made up of, a polysaccharide is made up of too many monosaccharide units. What does it mean, ma'am? For example, imagine I am your teacher and I am holding hands with 30 students that are watching my live right now. Okay? But I am one individual unit, right? So my individual unit, I am a monosaccharide, you are a monosaccharide, your friend is a monosaccharide, everyone forming a chain is a monosaccharide, but because we are in one single chain, arranged in a one single chain, we constitute a polysaccharide whole together. So because a chain is made up of individual atoms or individual R's, so individual R's is a monosaccharide, the longer chain formed is a polysaccharide. It's called a polysaccharide. Right. Now if I want to break the monosaccharide units, for example, if I want to break from here, okay, for example, a polysaccharide is made up of 4 monosaccharides. Can you see these are 4? 1, 2, 3 and 4. 4 monosaccharides. So can you see 4 monosaccharides units are actually connected with just 3 bonds, right? So for joining 4 monosaccharide units, I need 3 bonds. Therefore, even their breaking will involve breaking of 3 bonds. Therefore, to break 3 bonds, I will need H2O molecules. How many? If there are 4 monosaccharides, then I will need 3 water molecules to break them, because 3 bonds are going to be broken down, right? So 3 water molecules will get broken down. Similarly, understood this concept? Now for a polysaccharide contains n units, n-1 H2O molecules are required for hydrolysis. Remember this point. If there are n units of monosaccharide, one lesser amount of water molecule will be required to break them into individual monosaccharides. Okay? Next question. Next part is monosaccharides. Now what are monosaccharides? But again, do not get confused. Monosaccharides is again not made up of a single carbon, but it is made up of a carbon chain. For example, this is a carbon chain of 4 carbon atoms, right? But this carbon chain will never break down by water. Okay? This will always remain intact. That is why it is called a monosaccharide. Monosaccharide does not mean that it is only made up of one carbon. It can be made up of a number of carbons. ठीक है? Generally, it is made up of, monosaccharides are generally made up of 3 to 7 units, 3 to 7 carbon atoms. Remember this, 3 to 7 carbon atoms it is generally made up of. ठीक है? In monosaccharides again, the functional group can either be an aldehyde group or a ketone group, right? If it is an aldehyde group, it is called a aldohexose, and in ketone group and 6 carbon atoms are present, it is called a ketohexose, correct? And these are very, very important from the point of view of your exam. In your exam, mostly aldohexoses. For example, glucose, mannose and galactose is asked. From ketohexose, fructose is generally asked. So we will study them one by one. Number first is your glucose molecule. Let us understand how to prepare the glucose molecule. Again, this was your JEE 2024 question. This direct fact-based question bacha was asked in your exam. So can you see how do you prepare glucose? So by the hydrolysis of cane sugar, we actually prepare glucose, bacha. ठीक है? But somebody is asking, ma'am, why there is only 3 to 7 carbon in monosaccharides? Bacha, because this is how it is present naturally. You and I do not have any control in it. Okay? Because all these carbohydrates, the food that we eat, is actually present naturally. So how it is found in nature, scientists have just given you the data accordingly. So the monosaccharides units generally consist of 3 to 7 carbon units. Okay? Next is preparation of glucose. We are studying about the preparation of glucose. So hydrolysis of cane sugar is the number one thing. How do you hydrolyze it? So your cane sugar is bacha what? Your sucrose, the chini that you eat in the morning. The chini that you eat has this formula C12H22O11, and when you dissolve it in water in the presence of acidic catalyst, then you get glucose and fructose as your products, because cane sugar is actually a disaccharide. It means it is made up of 2 monosaccharide units called glucose and fructose. Remember this. Okay? So cane sugar is a disaccharide made up of 2 monosaccharides, glucose and fructose. So when I dissolve it in water, when I do it hydrolysis, I get glucose molecule. Hence, it is a preparatory method. Next preparatory method which is asked in your JEE exam was which enzyme actually converts your cane sugar into glucose. The enzyme name is bacha invertase. So you can either use the water and the catalyst, or you can use this enzyme directly on your cane sugar and get glucose and fructose as the products. So the enzyme is invertase. Remember this. Next commercial method to prepare glucose is what? You just take a starch or a cellulose. Starch or cellulose is a polysaccharide made up of glucose units. Okay? So you take a starch or glucose ki n units. If there are n units, then I would need n minus 1 units of water molecules to break down the bonds, and what I will get are n units of glucose. Okay? And it is done commercially with dilute HCl, dilute H2SO4 at 393 Kelvin and 2 to 3 atmospheric pressure. So this is a commercial method of preparation of glucose. Next, evidence of glucose structure. Now I know what is the molecular formula for glucose. It is C6H12O6. But how will I know the structure? Ma'am, how do scientists figure out that glucose molecule has that structure? Okay? So first of all, they found out their molecular formula. And how did they find out the molecular formula, bacha? Using mole concept. Whatever you have learned in mole concept, like you have learned mass percent, what do? You take glucose and then you burn it. So when you burn it, or when you do combustion of glucose, what will happen? CO2 and H2O will be released. So you can measure the amount of CO2 produced, you can measure the amount of H2O produced, and then by using the empirical formula which you learned in mole concept, you can calculate the exact percentage of carbon, of hydrogen and oxygen, and you can exactly calculate the molecular formula. Remember that. In mole concept used to do that. So using exact same technique, the molecular formula of glucose was determined. Okay, now I know the molecular formula. Now I want to know the structure of it. So what is the structure? So what I did, I took the glucose and I reacted with HI. HI is what? It is a very good reducing agent. Why? What is a good reducing agent? Which can easily give away H plus, right? Which can easily give away hydrogen is a good reducing agent. Okay, so HI is a molecule formed between iodine and hydrogen. Do you know hydrogen is a smallest molecule, smallest atom, and iodine is a very big atom, right? Because iodine is at the lowermost of the periodic table. So the bond between a bigger atom, which is the iodine, and a smaller atom, which is the hydrogen, is always a very weak bond. Why? Only stronger bonds are formed between two similar atoms. For example, when I join two hydrogen, two oxygens, those are similar atoms, same size, smaller size atoms form stronger bonds and larger atoms form weaker bonds. Okay? So this will be very weak, hence it is very easier to break down this bond, and hydrogen is released very effectively. Hence this is a very good reducing agent. So what does it do? HI, because it's a very strong reducing agent, it reduces the entire molecule, and what I get is a normal hexane. Okay, so because I'm getting a normal hexane means what? That all the carbon atoms, the 6 carbon atoms, 1, 2, 3, 4, 5, 6 are arranged in a single chain, in a straight chain. There is no branching here. So this proves that all the carbon atoms are present in a straight chain. So this first reaction proves this. Next, move on to the next. Next evidence for the structure of glucose, what we did, we took the glucose and I tried to react it with this NH2OH hydroxylamine and your HCN molecule. Now what happens, because these two molecules react extremely good with your carbonyls. Remember, either your ketone or your aldehydes. Okay? They react easily with both the carbonyls, and hence what you get an oxime with hydroxylamine and a cyanohydrin with your HCN molecule. So what does this prove? It proves that that your carbon chain actually has a carbonyl group present in them. Now what kind of carbonyl? Is it an aldehyde or is it a ketone? We don't know yet. This just proves that a carbonyl group is present. That is it. Next is, now what I did, I took the glucose and I tried to react it with bromine water. Bromine water is a mild oxidizing agent. Remember this. It is a mild oxidizing agent, meaning it cannot oxidize ketones, but it can only and only oxidize aldehydes. Now because it did give me a gluconic acid. Gluconic acid is what? Just that your CHO groups get converted into COOH. Nothing else gets affected. Everything else remain intact. So the acid that you get is gluconic acid. Now I know, because bromine water is able to oxidize the glucose, it means that glucose has a aldehydic group. So this reaction proves that an aldehyde is present in my glucose chain. Next reaction is when I try to react it with concentrated HNO3. It is again a very good oxidizing agent. So what product do I get? I get a glucaric acid or a saccharic acid. Same thing. You can call it glucaric acid or saccharic acid. They are the same name. They are different names for the same thing. Okay? Now this is a strong oxidizing agent. Remember this. This is a very strong oxidizing agent. Hence it oxidizes, obviously your aldehyde it oxidizes, and also it oxidizes primary alcohol. What does it oxidizes? Primary alcohol. So this proves the presence of a primary alcohol also, because we are getting a saccharic acid. Okay? So now we know this. Now the next thing is how many OH groups are there. Now we need to find out how many OH groups are there. So I try to react it with acetic anhydride. The structure of acetic anhydride bacha is this. So I try to react acetic anhydride in pyridine, and what acetic anhydride do? It replaces all the hydrogens from the OH groups. All the hydrogens from the OH groups, and it gets attached here and forms a pentaester groups. This proves that my compound has 5 OH groups attached to it. This proves 5 OH groups are attached. Remember this. Okay, so now what we have concluded? We have concluded that our compound has 5 alcoholic groups, 1 aldehydic group on, and they are present on different carbons. Why? Because this is a stable structure, right? If 2 OH groups, for example, if 2 OH groups are present on the same carbons, this is never stable. Hence, because the structure is stable, we conclude that the OH groups are present on different carbons. Okay, and the 2 OH groups on, okay, this I have concluded. So because now I know aldehyde group is always a terminal functional group, meaning what? That it will always be present at the end of the chain. Aldehydic group, your acid group, these are some of the groups which will always be present at the end of the chain. So I know that this, for example, I added CHO to the end of the chain first, then I attached 5 other carbons here, and to the 5 other carbons I have attached OH, because I know one of the carbon has primary alcohol, so this one will be the primary alcohol. So this is the structure that I conclude based on the reactions I just conducted, that there is an aldehydic group and 5 OH groups are present on my carbon chain. Now, but this does not give us the stereochemistry of glucose. The stereochemistry of glucose was actually given by another scientist called Fisher scientist, who confirmed what are the stereochemistry of glucose. Meaning what? For example, I do not know that C, OH and H. Can you see all these are bacha 1, 2, 3 and 4. All these are what bacha? These are all your optically active carbon, because all the atoms present, all the atoms attached to this carbon are different, and the carbons all are sp3 hybridized. So 1, 2, 3, 4 carbons are all your optically active carbon. So I do not know what is the spatial arrangement of OH around the carbon atom. So the spatial arrangement was given by Fisher, and he concluded that the structure of glucose looks like this. This is a carbon backbone with 4 different 4 chiral carbons. 4 chiral carbons means what? How many configuration or how many stereoisomers are present? So how do you calculate stereoisomers, bacha? Stereoisomers are calculated by this formula, which is 2 to the power n, and n is what, bacha? N is your number of chiral carbons. Okay, number of chiral carbons. As we know, this has 4 chiral carbons, so 2 to the power 4 is equals to 16 stereoisomers are possible for this glucose molecule, and this is the final structure of glucose molecule given by Fisher. Okay, and only one of them is positive D-glucose. Okay, bacha, what is positive here? Positive means what? Positive means that it rotates the PPL light in the right direction. Remember that. Only positive, only plus sign or your smaller d sign, smaller d, or your negative sign and smaller l denotes the optical activity. It denotes the bacha optical activity. Remember this. Capital D, the capital D that is written here has no relation with the optical activity. Capital D represents something else which I am going to tell you right now. But right now remember, the positive and the negative and the small d and the small l represents the rotation of the PPL light. But the capital D does not represent that. What capital D represents, I will tell you in just some time. Okay? Next is the stereochemistry part. Now we are going to learn about what is the capital D and the capital L, ma'am, which you have mentioned. So, bacha, as I just told you that the simplest, the smallest carbohydrate chain need to be made up of 3 carbons. So, this is the simplest glyceraldehyde made up of 3 carbons. Number 1 carbon, number 2 carbon and number 3 carbon is your simplest carbohydrate, which is made up of, bacha, 3 carbon atoms. Remember this. Okay? And in this, if on the second last carbon, can you see this is the last carbon, CH2OH is the last carbon, and this is your second last carbon, and if on the second last carbon OH is present on the right hand side, then it is a D. glyceraldehyde. And if the OH is present on the left hand side, then it is a L-glyceraldehyde. Simple. This is the only classification. Okay? And this has nothing to do with the rotation of the PPL light. This capital D and capital L has nothing to do with the rotation of PPL light. Only your small d and small l tells about the rotation of the PPL light. This is just some other classification that we have given according to the nomenclature. Okay? Ab, can you see that this aldehyde, bacha, this aldehyde, this carbohydrate which is your glyceraldehyde is actually polyhydroxy. Can you see? 2 OHs present, which means it is polyhydroxy. It is optically active, yes, and it is the simplest, and it has a aldehyde group present. Hence, it satisfies the definition that we began with, the definition of the carbohydrate which we begin with. It satisfied it actually. Okay? So this is a polyhydroxy aldehyde, and this is a D-glyceraldehyde and L-glyceraldehyde. Understood this concept? Now let's move on to the next, which is a sugar molecule tree. So with this tree, what is this? This is just a funda to make you understand the structures, to make you actually remember all the structures which are structure of carbohydrates asked in exam, which I have come up with the term called the sugar molecule tree. For example, we started with D-glyceraldehyde. D means what? That the OH is present in the glyceral. This is a glyceraldehyde molecule, right? Where the OH is present on the right hand side. Now when I start with D-glyceraldehyde and I want to increase the carbon atoms now. This is made up of 3 carbon atoms. Now with this I want to make a 4 carbon atom carbohydrate. How can I do that? Now I will attach, can you look at this molecule? In this molecule I will attach a carbon atom here above this. Above this I'm going to attach a carbon atom here, and to this now again I have to attach a hydroxyl group. Now if I attach the hydroxyl group on the same side, which is on the right side, then its name is D-erythrose. But if I attach the OH group on the left side, then its name is D-threose. Why again it is D, bacha? Because the D, the capital D only depends on the very last, the second last carbon atom. The D, this D nomenclature only depends on the second last carbon atom. If on the second last carbon atom OH is on the right side, it will be a D molecule, and accordingly we will give the names. This is D-threose, where the other hydroxyl group goes to the left side, otherwise it is D-erythrose. Understood? Now with D-erythrose was when both the OH groups were on the right hand side. With this D-erythrose I can again come up with molecules. This D-erythrose is made up of 4 carbon atoms. Now with this 4 carbon atoms I want a 5 carbon atom carbohydrate. How can I do that? I will just attach another. Let me change the pen color. I will take green color now. So here I will again attach an atom over here. I am doing nothing. I am attaching another carbon atom over here. And if I do that, the OH can go to the right side, and if it goes to the right side, its name is ribose, and if it goes to the left side, its name is arabinose. Understood? Its name is arabinose, and it's again a D molecule. Why? Because the second last carbon has the OH group on the right side in all the cases. Correct? Okay. Next. Sugar molecule T. Now from this D arabinose. Now from this D-arabinose, what am I trying? I'm again choosing another pen color. So D-arabinose was what, bacha? Where these two were on the right side, this OH was on the left side. Through this D-arabinose, I am again making, this is a 5 carbon sugar. From 5 carbon, I want to make a 6 carbon carbohydrate. What am I doing? I'm attaching another molecule of carbon over here. So if I do that, the OH can go to the right side or to the left side, right? If it goes to the right side, the molecule is glucose, and if it goes to the left side, the molecule is mannose. So now in this way you can remember all the important structures. This is a very important sugar molecule tree. If you try to draw the structures in this fashion, starting from glyceraldehyde to erythrose threose, and then to your arabinose, and then your glucose mannose, then you will never ever forget the structures of all these carbohydrates. I have made it extremely easy. You just need to practice in your notebook 3-4 times and it will be etched in your brain. That is a promise, because children have been doing that, following this, and this always works. Bacha. Now let's talk about epimers. Now what are epimers? This kind of questions will be asked in your exams. So bacha, look at the molecule of erythrose and threose. Can you look at these molecules of erythrose and threose over here? So what happens here? So here, can you see there are 2 chiral atoms here and there are 2 chiral atoms here. Okay, so can you see what is the difference between these 2 molecules? The only difference is that this OH is on the left hand side here, and here the OH is on the right hand side here, and here the OH is on the left hand side here. So this is the only difference between these 2 molecules, right? So this is the only difference. So these are called your epimers. This difference of your arrangement of OH, whether it is on the right side or the left side, no matter on whatever carbon that difference is there, these molecules bacha are called your epimers. Okay? So bacha, what are epimers? Let us look at the definition. These are diastereomers that differ in configuration at only 1 chiral carbon are called epimers. Can you see bacha? These are diastereomers. Diastereomers means what? They have the same molecular formula, but they are not mirror images of each other. Can you see? These have the same molecular formula, same connectivity through this carbon. Through this carbon, what is happening? One H is connected, one OH is connected. Similarly, through this carbon also, one H and one OH are connected. The connectivity is same, but the spatial arrangement is different and they are not mirror images of each other. I cannot superimpose erythrose and threose on each other and get a superimposed product. Hence, these are called diastereomers, and hence these are called bacha what? Your epimers. Okay, understood this? So every bifurcation we created made 2 epimers. For example, ribose and arabinose were epimers. Look at the structure of ribose and arabinose. Can you see? This is ribose 4 carbon sugar. Arabinose is also 4 carbon sugar. They have the same structure till here. Till here they have the same structure, right? But only on this carbon, which is your C2 carbon. The C2, can you see? This is C1 carbon, this is C2 carbon. On the C2 carbon, their configuration changes. So hence these are C2 epimers. Can you see that? Similarly, your glucose and mannose again are your C2 epimers. Can you see? Only and only on your C carbon 2 position, the position of OH, the configuration of OH is changing. Hence, these are C2 epimers. Understood? Understood. And also, epimers are always diastereomers, meaning what? They are not mirror images of each other. Remember that? And on whatever carbon the exchange is present, we are going to tell it as C2 epimers, C3 epimers, C4 epimers, whatever epimers accordingly. Okay? Now let's talk about enantiomers. What are enantiomers, bacha? Which have the same molecular formula, same connectivity, but and also they are mirror images of each other. Meaning what? Meaning what? For example, the D-glucose and the L-glucose are mirror images of each other. Can you see? Here the OH is on the right side, here it is on the left side, right side, left side, left side, right side, and it is again right side and left side. Can you see? This is an exact mirror image of this molecule. So D-glucose and L-glucose are exact enantiomers of each other. These 2 molecules are exact enantiomers of each other. Okay? Now what we have concluded till now, that the glucose structure that we have made after the Fischer projection, after he has given us a stereochemistry, we have understood that the glucose structure has a straight chain. It is a straight chain molecule. But there are some reactions which conclude that actually glucose is not a straight chain molecule. So what are the failures of the straight chain structure? The number first failure is, bacha, that the glucose, what group does it have? Glucose has a aldehyde CHO group present to it. But CHO group is a carbonyl group. So it should show all the reactions that are shown by any other aldehyde group, right? For example, aldehydes show 2,4-DNP test, they show the Schiff base test, they show the sodium HSO3 addition product, but your glucose do not show any of these reactions, any of these tests. So it actually begs the question, does glucose have a straight chain structure? Next is the pentacetate of glucose. When we make a pentacetate of glucose, does not react with the hydroxylamine to form an oxime. Okay? So these two reactions, because of these two things that happens, we have a question mark on whether the structure which we have proposed for your carbohydrates, for your glucose, is correct. ठीक है, दो straight chain or direct reaction forms oxime, cyclic structure doesn't. Both these observations indicate the absence of free CHO group. ठीक है, so what we have concluded in this scenario, that the CHO group, the aldehyde group, is not free through these reactions, because if it is not giving the 2,4-DNP test, if it is not giving the Schiff base test, if it is not giving the sodium hydrogen sulfate test, it proves that it does not have a free CHO groups. That's why it's not able to react. Right? Now moving on to the next. So therefore, and also, what are the other things that were observed? There was also observed that when I take a glucose molecule, what happens? If I try the crystallization of the saturated solution of glucose at 303 Kelvin, then I get alpha glucose. Okay? Then what product I'm getting? I'm getting alpha glucose, which have some different melting point, while beta glucose has a different melting point. And how is beta glucose prepared? By crystallization of hot and saturated solution as 371 degrees Celsius. It is prepared at room temperature. It is prepared with boiling point of water. Remember this. So what I am getting? I am actually getting two different kind of things when I am trying to prepare glucose. I am actually getting two different kind of things which have totally different melting points. Hence it raises the question, like, what is the actual structure of glucose? Okay. Next is this. Now that after having these observations, scientists propose a cyclic structure of glucose. And what did they do? They draw the straight chain structure of glucose. This is a straight chain structure of glucose. Okay. And through this straight chain, because we just concluded that the aldehyde group is not free. What is the aldehyde groups looks like? It looks like C double bond O and H. Correct? This is how the aldehyde group looks like. Now what they did, they actually tried to make a ring, a hemiacetal out of this aldehyde group, because we just observed that it is not free. So what happens? This is the aldehydic carbon which gets converted into an OH and H, and to the another oxygen comes out of here and it gets attached to the carbon 5 of your chain. So can you see a hemiacetal? What it is forming? It is forming, bacha, a hemiacetal ring. What are we doing in this? In this we are forming a hemiacetal ring. I have done nothing. So this was the structure of the glucose molecule. There will be OH, there will be H, correct? This kind of structure. So what I did, I actually tried to react it with water. So whenever I try to react it with water, what is happening? So one OH is getting attached here, and this O actually forms a cycle with the 5th carbon atom. Okay? So this kind of cyclic structure was proposed, and if the attached OH is on the right hand side, it is called alpha D glucose, and if the attached OH on the first carbon is what, which are the first carbon is your functional group carbon where the CHO was present. So the CHO carbon gets converted into the COH and H, where the OH, if it is on the right side, it is called alpha D glucose, and if it is present on the left side, it is called beta D glucose. It is the alpha cycle, it is a beta cycle. Can you see the beta cycle is actually more in percentage? It means it is 64% available, it is 36% available, and your straight chain glucose structure is only a 0.02% available. Meaning what? That the straight chain and the two cyclic chain, which is the beta chain and the alpha chain, are always in equilibrium with each other, no structure is the fully correct structure of glucose. The correct structure of glucose is somewhere in between these three structures. Okay? And their equilibrium is somewhat like this. A beta is 64, alpha is 36, and your straight chain is 0.002%. Okay? And alpha and beta forms can interconvert via straight chain structure. Also remember that they are interconvertible structure, meaning they have same energy. Correct? Only those can interconvert, right, which have the same energy. Remember this thing? Everybody understood this thing? Everybody understood this thing, bacha? Next thing. Next is the proof of the cyclic structure. So what is the actual proof of a cyclic structure? ठीक है? अब always remember what is the meaning of hemiacetal and what is the meaning of acetal. So if to the same carbon, look at this carbon, everybody just look at this carbon. If to the one carbon an OH group and the OR group are attached together, it is called a hemiacetal carbon. Remember this. If to one carbon, see, can you see, to this carbon only one OH and one OR is attached. Hence it is a hemiacetal. And if to the same carbon two OR groups are present, then it is called a acetal carbon. Remember that. Do you now know the definition between the acetal and hemiacetals? And how do you prepare acetal and hemiacetal? When I try to react a secondary alcohol with aldehyde, then I get, or when I try to react two alcohols, okay, two alcohols with aldehyde, I get acetal. And when I react only 1 mole of alcohol with aldehyde, I get a hemiacetal compound. Okay? Now you know what is the structure of hemiacetal and why am I calling this structure? Why am I calling this a hemiacetal structure? Can you see, to this carbon atom, one OH group and one O, and this is connected to the entire chain of carbon. So one OH and one OR group is attached to this same carbon. Hence it is called a hemiacetal ring. Remember this. Can you see again here, to this carbon there is one OH group here, right? And to the same carbon and again O and R group is attached. This is what? This represents that this oxygen is attached to the entire this carbon. Hai na? So this is again a R group attached. So this is a hemiacetal ring. Understood this concept? Now what is again another proof of cyclic structure? So bacha, I have made you understand this. Now do you know the carbon in CHO? Because CHO has this kind of structure. This is H and here again another R group is present here. So this carbon is actually sp2 hybridized, but the hemiacetal carbon is actually sp3 hybridized. So when it gets converted into a cyclic form, into a hemiacetal form, your functional group gets converted, then your glucose actually becomes a sp3 hybridized structure. Remember this thing. What is happening? Your carbon 1 is getting attached to carbon 5 through oxygen bonding. Okay? And it is forming a hemiacetal ring. Okay? Understood everybody? Understood everybody? I have made you understand everything which is given in this slide. Whatever I have taught you is given in words. So you can just download the PPT from the Telegram channel. After this session is over, I will send on the Telegram channel and you can all see and look at the notes will be there for you. Next, cyclic structure of glucose. As I told you, there are two structures and one is the alpha and the other is the beta form. Correct? Now, bacha, these alpha and beta forms, how are they prepared? They are prepared by the first carbon. The first carbon, bacha, was what? The alpha and beta forms are prepared by converting the functional group part, which is the aldehydic part. Correct? The functional group part, I was converting it into hemiacetal ring. Correct? I was converting into hemiacetal ring. I was doing that. So therefore, whenever the functional part, the functional group part gets converted into hemiacetal form, it gives rise to alpha and beta forms. In alpha and beta forms, again what is happening? Your OH group is actually either coming to the right hand side or to the left hand side. Now do you remember? Go back to the definition of epimers. What were epimers? Whenever the position of just one OH group was changing, I called it epimer. Remember that? That was called epimer. But here, Because we are actually looking at the position of the OH of the carbon which was your functional group carbon. So this is a special case. So anomer is a special case of epimer bacha that differs in configuration specifically at the hemiacetal or the acetal carbon. So this is again a kind of like your alpha and beta. Okay, again go back to the alpha and beta structure. Or is there alpha beta structure here? Let me see. Alpha beta is not given here. We'll go back to this thing. Okay. Again, look at the structure of alpha and beta glucose. So this is alpha glucose here. Look at the alpha glucose and look at the beta glucose. Okay. And what is happening at the alpha and beta? You can call it, ma'am, these are C1 epimers. Can you call it that? Right? But bacha, because now I have made a hemiacetal ring out of the functional group carbon, hence this OH and OH placement, the difference in configuration here, this kind of isomerism is actually called anomers. What are they called? Anomers. Okay, so it is again a very, very special kind of epimer only. Okay, you can call it epimers, but the correct name for it, the more correct name for it are anomers. So anomers are any of those compound where the functional group, where we are looking at the OH of the functional group and then we are trying to name the isomerism. Correct? So whenever you are looking at the functional group, just call it anomers and not epimers. That is it. Everybody understood it? Okay? Next we have done this. Now drawing the cyclic structure. We have drawn this cyclic structure which is called the hemiacetal form. Through this hemiacetal form, let us make a cyclic ring structure. Now look at this structure again. Let me select a pen color. Okay? Ab can you count how many atoms of ring? Like the ring should contain how many atoms? So can you see this is the first carbon? Okay? First atom, second atom, third atom, fourth atom and fifth atom. Okay? So 5 carbon chain and this is again a oxygen. So oxygen is your heteroatom. So this is the 6th carbon atom. So there 6th atom, right? So therefore it should be a 6-membered ring because 6 things are attached in a ring. So what I've done, I've made a 6-membered ring and the 6th member is actually an oxygen atom which is a heteroatom. So I've attached oxygen here. Now can you see these are OH groups present here. So whenever the OH is on the right hand side, so after forming this ring, whenever the OH on the right hand side in the ring, they will come on the downward side of the ring. Correct? So whatever OH, this on the first carbon, this is the first carbon. The first carbon is also called the anomeric carbon. Remember this. The first carbon is called the anomeric carbon because it has the functional group carbon, because it contained the functional group carbon, therefore it is called the anomeric carbon. And if the OH group is on the right hand side, it will come downwards. Again on the second carbon it is on right hand side, so it came downward. On the third carbon the OH is on the left hand side, hence it came upward. And on the fourth carbon it is right hand side, it came downward. On the fifth carbon actually we have done what? We have attached it with oxygen, and the sixth carbon actually comes over here. Okay, so this is how you draw alpha D glucose. Why? Because the first anomeric OH is on the right hand side. Now let us draw the beta D glucose. So when we have drawn the structure of alpha D glucose, just interchange the OH and H on the first carbon atom. So when we interchange the H and the OH in the first carbon atom, we get a beta D glucose structure. These are all the other things remain exactly the same, hence these are called bacha what? Hence these are called your anomers. Everybody understood it? And the two forms, which is the alpha D glucose and the beta D glucose, are always in equilibrium with each other, as I just told you. But this is actually 64% and this is 36%. Hence beta D glucose is the most stable isomer. Okay? And alpha D gluco, and this is also called alpha D glucopyranose. Why? Because this structure which we have drawn here, this is a structure that we have drawn of glucose, right? This structure is actually a derivative of another structure called pyran. Okay? So because this structure is a derivative of pyran structure, hence these molecules are called pyranose. Okay? Hence it is called glucopyranose. This one is called beta D glucopyranose. Okay? Understood these things? Next thing, stability. As I just told you, because beta isomers are present in much larger numbers, it is 64%, hence it is more stable isomer. And why is it that the case? Because bacha, in the beta form, as you all know, I just draw the structures, and when I was showing to you alpha and beta isomers, I draw this cyclohexane kind of ring. But in actuality, in reality, this is again not how the molecules actually exist in real life. In this hexagonal shape, the rings do not exist. Rings actually exist in this chair form. Can you see? This is called the chair or a boat form. So this is actually chair or a boat form in which these things exist. And if your OH, can you see in the alpha D glucose, the OH on the first carbon is actually at the it is on the axial position. Okay? This position bacha is called your axial position. This is called the axial position, and this position which is on the tilted side. Okay? Can you see this is on the tilted side? This position of OH is actually called the equatorial position. So the axial OH actually causes too much steric hindrance, and hence it is unstable. So whenever a larger molecule is actually present at the downward position or the upward direct position in the chair or boat form, it is unstable. But if it is present on the equatorial position, it is actually stable. So the larger group, the OH is a larger group than hydrogen, right? So the larger group should be on the equatorial carbon, and hence this beta D glucose form is actually a much more stabler form than your alpha D glucose. Okay, and again your 5 and 6 membered hemiacetal rings are stable due to ring size, as we've always learned in our organic chemistry that 5 and 6 membered rings are actually stable rings. That's why these structures are actually stable. And now I told you why beta D glucose is more stable, because the OH is on the equatorial position. Okay? Yes, bacha, chair and boat form are different, but they get interconverted into each other, right? And if the OH is present on the equatorial position in these forms, then that structure is actually a stable structure than your axial position. Yes, they are different forms. You are absolutely correct. This form which I have drawn over here is the chair form. A boat form actually looks like this. This is the boat form, and the structure that is drawn over here, this is actually called a chair form structure. So the structures explained here are your chair structures, not your boat form structure, because boat form is again your unstable structure. Chair is a stable structure. Remember this thing. Okay? Next question. Next is about your mutarotation. Mutarotation bacha means what? It's simple thing that whenever if I put the PPL light through my glucose, then what will happen to it? Will it rotate on the right direction or in the left direction? What will happen to it? So now I've understood that my glucose molecule is actually a little complex, that it is not, it doesn't have one structure to it. It is actually a mix of alpha D glucose, of beta D glucose, and of the linear structure. It is actually a mixture of all of these, right? So the alpha D glucose, the alpha D glucopyranose actually rotates the PPL light in this much, plus 112.2 degrees, and beta D glucopyranose rotates the PPL light in again the positive, the right hand side direction, but its rotation is a bit less, plus 18.7. But we know that the beta D glucose is actually more stable structure, hence it is formed more. Hence the optical activity at equilibrium. Equilibrium means what? When both the structures are at equilibrium with each other, then the optical activity observed is actually 52.6 degree in the positive direction, which means it rotates the right in the right direction. This process is called bacha mutarotation. What it is called? What? Mutarotation. Everybody understood? Now let's move on to the next structure, which is your fructose structure. This is again a 6 carbon carbohydrate, remember this, but here the functional group present is a ketone group, and ketone group is always present what, somewhere in the middle, and it here in fructose structure it is present on the second carbon. The ketone group is present on the second carbon, and the structure of fructose is somewhat like this. Everybody is seeing the structure. The CH2OH, there are two primary alcohols, and then there are, how many chiral carbons does fructose have? Can anybody tell me? I can see number 1 chiral carbon, 2 chiral carbon, and 3 chiral carbons. So fructose actually have 3 chiral carbons. Hence, how many stereoisomers does it have? How many stereoisomers does fructose have? So it is always 2 to the power n. So how many chiral carbons? 3 chiral carbons, so 2 to the power 3. So 2 into 2 into 2, which is what? 2 to the 4, 2 to the 8. So it has 8 stereoisomers. So fructose has actually 8 stereoisomers because it has 3 chiral carbons. It is a levose sugar. Levose means what? It is a ketohexose, means it is a ketone ketone functional group. Hexose means 6 carbon sugar. Levose means it rotates the ppl light in the left direction, which means it has a negative sign, which means it rotates the ppl light in the left direction. Okay? Now again, as the OH is on the, as the second last OH, always remember, always look at the second last OH. The second last OH, as it is on the right hand side, can everybody see? As it is on the right hand side, it is a D sugar, therefore it is a D minus fructose. Minus why? Because fructose always rotates the ppl light in the left hand side direction, so hence minus is for the ppl light. D is because the OH on the second last carbon is on the right hand side, hence a D fructose structure. Now let us look at the anomers. As we saw the anomers of glucose, which was alpha anomer and beta glucose, right? Fructose also have alpha and beta fructose. Again, what happens? Anomers are created by the functional group. Always remember this. So the functional group here is now on the second carbon. The ketone group is on the second carbon. Everybody can see. Now on the second carbons, what happens? Here, see, this is your first carbon, which is a CH2OH. So CH2OH comes here. The first carbon comes over here. And now this is your second carbon. On the second carbon, if the OH comes on the right hand side, then it is a alpha fructose, and if the OH groups comes on the left hand side, can you see, it becomes a beta fructose. So anomers are getting decided by what? Anomers, remember, anomers are only and only getting decided by the position of functional group. So the aldehyde in the glucose case was on the first carbon. Hence, the anomer alpha D glucose and beta D glucose were C1 anomers. Here, the anomers are always C2 anomers. Why? Because the functional group here are present on the second carbon. Okay? Everybody is understanding this? Beta chiral carbon is anything. For example, to the carbon, somebody is asking, ma'am, what is chiral carbon? So, if to a carbon, 4 different groups are attached, A, B, C, D. If 4 different groups are attached to the carbon, then that carbon becomes a chiral carbon. Okay? 4 different groups, 4 different bonds should be there, only and only then it will be a chiral carbon. It means it will show optical activity. What is the meaning of chiral carbon? That it will rotate the ppl light. Okay? Understood? Alpha D fructose and beta D fructose means what? When the OH is on the right side, it is alpha, it is on the left side, it is beta fructose. Now this is again the hemiacetal form of fructose. Why am I calling it a hemiacetal form? Can you see, to this carbon atom, one OH group is attached and one OR group is attached. This is the OR group. This group bacha is the OR group. Why? Because this oxygen is connected to the carbon of fifth carbon. Can you see? So the second carbon is attached to the fifth carbon through the oxygen group. So how many membered ring will be formed in this case? Who can tell me? So can you see, this is first carbon, second carbon, third carbon, fourth carbon, and this is the fifth atom that gets attached. Hence in fructose we will form actually a 5-membered ring structure. 5-membered ring structure will be formed. Again, how to write? This is a structure of a 5-membered ring, always formed. This ring is called bacha a furan ring because it is derived from this structure which is called furan. It is a derivative of furan, hence this ring is actually called a furanose ring. So fructose ring is called furanose ring, just how the glucose ring was called a pyranose ring. Always remember this thing. Now next is bacha what? Now next is how to actually write the OH group. Can you see? This is the second carbon. So here in fructose, the second carbon is actually your anomeric carbon. Everybody can see, and this is the first carbon. So if on the second carbon the OH, can you see it is on the left hand side? If it is on the left hand side, it comes upward. Again the same funda will be followed. When the see here the H is on the right hand side, so on the third carbon the H will come downwards. So whatever is on the right side will come on the downwards of the ring, and whatever is on the left side will come on the upward region of the ring. Everybody understood this? Yes, bacha, this is actually useful for your CBSE JEE exam. Obviously, it is useful for CBSE because it is in your course. Bacha, everything I'm teaching you is really essential for your CBSE and JEE, because even now, as the pattern has changed, as you observed questions, looking at the pattern of a JEE exam, what we have observed is that, yes, bacha, this is useful. Now what we have observed looking at the exam pattern, that even your JEE is following the NCERT. Okay? So we will cover the NCERT. We are obviously covering the NCERT in this JEE session. So this is useful even for your CBSE board exams. Okay? Now let's move on to the next. So we have drawn the structure of fructose. This is a cyclic structure of fructose. Again, we are going to distinguish between alpha D fructose and beta D fructose. Or fructofuranose we can call it, or fructofuranose we can call it. Alpha means when the OH is on the right hand side, which means if the OH come downwards then it is alpha, and if the OH come upward it is beta. But they have given you again another way to identify alpha and beta D fructose, which is actually an interesting method, which is if the carbon, if on the first and the sixth carbon the CH2OH group are on the same side, then it is the alpha D fructose, and if they are on the opposite side, can you see here the first and the sixth carbon CH2OH are on the opposite side, means a beta D fructose. These are just identifying method tricks that they are trying to teach you. Okay, so these are just tricks that you can just keep in mind. Everybody understood? Beta, it will, somebody is asking, ma'am, will April shift be easier than the January shift? Then the answer is a big no. It will not be easier, it will be difficult. It is expected, like seeing the previous year trends, it will obviously be difficult, because till then you will all be done with every of your board exams, and even your NTA expects you to know much more and be much more stronger in your concepts. The easier attempt bacha is now gone. Now is the time for the difficult attempt of JEE. ठीक है? Next, fructose and glucose. So glucose and fructose actually show similar reactions. Now similar reactions means what? The alpha hydroxy carbonyls are known to show positive results for Benedict's test, Felling's test and Tollens test. So as we know, the aldehyde, the glucose has a aldehyde group. So we know that aldehyde groups will show positive Benedict test, Felling's test and Tollens test. Where do you learn about these tests? You learn about these tests in your carbonyls, right? In the carbonyls chapter. You learn about these tests in those chapters, right? So, I'm not going to teach you again. I'm just going to show you this slide. Can you see this slide? So, in Benedict's test and Felling test, bacha, what are these tests? These are again compounds which are copper 2 plus compounds. These are complexes of copper 2 plus, and in both these tests what is happening, you're converting copper 2 plus into copper plus. Okay, it means they're behaving as a good oxidizing agents because they're themselves getting reduced. So if it is see, if the control of Benedict's actually looks blue in color, and if it gives a positive test turns red, and if it is blue in color, a positive test turns it into red. Okay, it means what? It oxidizes the aldehydic part into a acidic part. Okay, so we have all learned about these tests, and again Tollens test is bacha what? tolerance test is bacha your complex of Ag plus ions. So your Ag plus ions are actually get converting into Ag0 ions. Remember this. So what is happening? Your Ag plus is getting converted, reduced into Ag0. This is again oxidizes your aldehyde group. Okay? And a silver mirror is formed. This is what a tolerance test actually looks like, and you actually read about in a much more detail in the aldehyde ketone carboxylic acid chapter. I'm not going to teach you from the very basic, from the very beginning, because it is expected. If you are learning with biomolecules now, it is expected that you know a little bit about these tests, right? Yes, bacha, you can watch it for NEET, JEE, CBSE, because the course is exactly the same. Now, next thing, bacha, is your Benedict's test, Felling's test, and Tollin test. I've already told you, but now that I know that fructose, ma'am, actually has a ketone group. So the ketone groups, ma'am, do not give positive Benedict test, Felling test, and Tollin test. These tests are only and only given by aldehyde group. No. Actually, Benedict's, Fellings, and Tollins, you are right that most of the ketones do not give all these tests. But if the ketone has what, bacha? If the ketone has alpha hydroxycarbonyls, means what? To the ketone. For example, this is a ketone group, and the carbon attached right next to the ketone group has a hydroxy group present on it, then it will definitely give a positive Tollins test, positive Felling test, and positive Benedict test. Always remember this thing. And because fructose has a ketone group in it, but it is also a alpha hydroxy carbonyl, right? Because OH groups are present, hence it will give positive tests of these. Next is glucose and fructose show positive tests for Benedict's, Fellings, and Tollins tests, which we have already discussed. Next is reaction of glucose. Now let's learn about some reactions of glucose. This is the structure of glucose, and when I try to reduce it with a mild reducing agent, can you see sodium amalgam in ethanol? It is a mild reducing agent. The things to take away from this session are what kind of reagents are we talking about, and what kind of reagents are they? Because they will not give you glucose structure next time. They can give you any other organic compound and ask you to reduce it with sodium amalgam and ethanol, and you must know that it is a mild reducing agent, and what it does, it just converts the CHO group to the CH2OH, which is a primary alcohol group. It doesn't reduce anything else. It is just reducing your aldehyde to your alcohol. Always remember this. And what product you're getting? You're getting a glucitol or a sorbitol product. This is again was asked in your JEE 2024 exam. What happens with a mild oxidizing agent if you try to reduce it? Now, if I actually use, instead of this, what I'm telling you to reduce glucose with HI. Now, HI is a strong reducing agent. We just discussed HI. HI, because it is a strong reducing agent, it will convert glucose into normal hexane. It means it has reduced every OH, and even your aldehyde and all the OH and all the alcohols in it has reduced it all and converted into a straight chain of hexane, because it is a very strong reducing agent. Remember this thing. Next is reaction with HCN. So we know that HCN reacts with your carbonyl groups, right? So if I try to react CHO with HCN, what will happen? Again another carbohydrate, again another ring will be formed, which will be the product that will be formed will have one extra number of carbon in it. Can you see? So this was my CHO group. This was my CHO group, and here some carbonyl chain was there. So I'm not drawing it all. And when I try to react with the HCN, so what will happen, bacha? What happens is your C double bond O. Your C double bond O was there. So with one O, the OH attached. With the other bond, the CN groups attached. And here the H is there. And here again the entire structure is there. So can you see that we have actually increased the number of carbon on your product? So we started with 6 carbons in glucose, but now I'm getting a 7 carbon structure. And here also, bacha, what I'm getting is a pair of enantiomers here. What pair of? Can you see that I'm getting a pair of not a pair of enantiomers that you can say, but you can say that you're getting a pair of products in this case. Why? Because the OH here can either go to the right hand side or to the left hand side of the product again. So we are getting, actually, because it's a chiral carbon, we're getting two kinds of addition products. Okay, everybody understood? Now next, reactions of fructose. So bacha, what is happening? This is the structure of fructose and I'm trying to react the structure of fructose with OH negative ions. Okay, understand this thing which I'm trying to tell you right now. Okay, very very clearly try to. Okay, try to. So OH is bacha what? It is a very very good nucleophile. And what is the purpose of a nucleophile? OH negative ion especially, it actually abstract H plus. Always remember. So this is very crucial from the point of view organic chemistry. In organic chemistry, you will be using OH minus a lot. So what is the first function of OH minus? That it abstract the H plus ion. So any hydrogen that is a very acidic hydrogen will get removed by this OH because it is a very very good great nucleophile. It abstracts hydrogen to itself and forms a H2O molecule. Okay, so now what is happening? Why is this hydrogen acidic, bacha? Because it is attached to a carbonyl group. Can you see? And carbonyl groups are a good electron withdrawing groups. Remember this thing, C double bond O. C double bond O groups are good electron withdrawing groups, and hence because it's a good electron withdrawing group attached directly to the carbon, to this carbon, hence this hydrogen actually becomes acidic. So this OH actually takes away this hydrogen and forms a ketoenol. Can you see? A ketoenol tautomerism is formed here. A ketoenol tautomerism. See, enol is formed, enol. So ketoenol tautomer is formed, and again what I am doing, again giving a OH negative to it. So which hydrogen is acidic now, bacha? This hydrogen is again more acidic. So it will take away this hydrogen and it will form what? It will form another product which is your CHO group will come here. So it has actually formed, able to form a glucose molecule. So it has formed one glucose here with the OH here, and the other OH actually goes to the right hand side and the other one goes to the left hand side, because there are two possibility of the arrangement of this OH. So these kind of D-glucose and D-mannose product are formed. So you can actually, through fructose, you can form a glucose molecule in a very basic medium. Remember this thing, okay? From fructose. So can you form glucose from fructose? Yes. So when I give basic medium, fructose get converted into glucose plus mannose. Remember this thing, because of the acidic hydrogen attached right next to the ketone group, it gets abstracted. Okay, everybody understood it? And this only happens because there is a presence of acidic hydrogen atom into it. Everybody is understanding this thing. Next is the intermediate has two vinyl. So this thing are not important. sp2 hybridized, you just know this. So this is actually gets converted into a sp2 hybridized carbon. You can read on the theory. I've explained to you every other thing. Now the reactions of glucose, the last reactions of glucose that we are going to study is the OSA zone formation. So what happens in this case, bacha? Okay, so what happens in this case, bacha, in the OSA zone formation, again some reactions are there which you can study on your own. I'm not going to explain it to you again. This is a very basic aldehyde ketonic reactions. OSA zone is get formed because it is a carbonyl group attached to it. Okay. And next is, we've already talked about what are hemiacetals and acetals. This is again a slide explaining the similar thing. Next is reaction of glucose is what, bacha? When you try to react with ethanol. So can you see ethanol? When I try to react it with ethanol, so what happens? This anomeric OH. This anomeric OH only gets converted into ET. So now what I have formed? This was a, bacha, this ring was actually a hemiacetal ring. This ring was actually a hemiacetal ring. Why? Because to this carbon one OH and to the same carbon one OR group is attached. Hence it is a hemiacetal ring. But when I react it with ethanol, I am converting into a acetal or a ketal product. Why? Because can you see here? Can you see OET is present here and OR is present to this carbon, one OR is present and the other OR is present here. Hence it gets converted into a hemi-acetal or a ketal carbon. Remember this thing. Similarly, I can do even acylation reaction. Now if I do alkylation of CH with CH3 in excess, what happens? All the OHs get converted, all the OHs that are present gets converted into OCH3, OCH3, OCH3 group. Similarly, I can even replace the OH with the acetyl group with the help of acetic anhydride. So all the OH here, what will happen, bacha? All the OH will get converted into the acetyl group, which is a penta-acetate beta-D-glucose group. Okay, now we're talking about bacha the disaccharides. To form a disaccharide, we need to join two mono. So the disaccharides units we are going to start in the next section. So right now we have covered a bit of the monosaccharides and all the reactions of glucose. In the next session that we're going to do, I will explain to you the disaccharides, proteins and nucleic acid in just one lecture, because explaining monosaccharides actually take a bit of a time because it's a quite new concept. But right now, because you've already understood what are monosaccharides, understanding disaccharides is nothing. We're just joining two of the units and we're going to study what are the structures of it, what are the structure of starch, cellulose, glucose, and proteins is extremely easy part and nucleic acid are even easier. And I'm going to share all the slides with you and you can go through them. This will be very, very useful for your preparation and you don't have to go through your NCERT once again, because language in the NCERT is a bit difficult. Hence, I recommend you to go through my notes, because these notes contain each and every tiny detail which is given in your NCERT. Nothing is missing out. And thank you for attending the class. I hope you liked it. This was your chemistry teacher, Nandini ma'am. Whatever feedback you have, whatever questions you have, you can let me know in the comment section below. Whatever chapter you want to study with me, we will study all together. Beta, timing of the second session, I will let you know. Right now, I have not scheduled it yet. Tomorrow, we are going to study about name reactions and reagents, because those are more important. Because if now that you have understood what monosaccharides is, right? We have understood the basic concept. So even if you go through the notes at this time, which I'm going to share in the Telegram channel, you're going to understand it, right? And again, I'm going to schedule another session, probably not this week, next week we are going to study it. So I am going to complete this chapter, do not worry, but I'm going to share the notes with you just in case you want to study it right now along with the same chapter, because I've already taken like 1.5 hours today. And thank you so much for attending the class. I hope you liked it. I hope you understood it. If you didn't understand, tell me that also in the comment section. Ma'am, what are you teaching? We're not understanding anything. Please let me know. Let me know what I need to change, what I need to do to help you guys better. What kind of notes do you want? Or are you satisfied with the content that you're getting? Are you able to solve all the questions with the things that I'm teaching you here? Because that's the only motive, the only purpose. Go through the PYQs, solve the questions and let me know if anything is getting missed out on here and you want to study and know more about it, but in the comment section, not in the live chat box, because live chat gets lost after this live ends. Take care. Thank you so much. Thank you for attending the class. Bye bye.